Have you ever stopped to wonder why you can remember what you had for breakfast yesterday, but you have no idea what you're going to have tomorrow? Or why things always seem to fall apart, get older, and decay, but they never ever spontaneously put themselves back together? It feels, well, obvious, right? But hiding behind that simple observation is one of the biggest, most mind-bending questions in all of physics, the arrow of time. Okay, let's get into it. Seriously, just think about an egg. You can crack it, scramble it up in a pan, no problem. But you will never see a pan of scrambled eggs suddenly pull itself back together into a perfect, unbroken egg. If you saw a video of that, you'd know instantly it was being played backward. It would just look wrong. That's our daily experience of time. It's a one-way street, always moving from the past to the future. But here's the real puzzle. The fundamental laws of physics that govern everything, they don't seem to care which way time is going at all. And this right here, this is the core of the problem. It's this incredible disconnect. See, down at the tiniest microscopic level, the rules for how atoms and particles behave are almost completely time-symmetric. If you filmed two atoms bouncing off each other and then played it in reverse, it would look totally normal. It's just as believable forwards as it is backwards. There's no built-in direction. And yet, up here in our world, time has this powerful, unstoppable one-way flow. So what gives? What's the missing piece here? Well, to solve this mystery, we need to find something in the universe that isn't reversible, something that only ever happens in one direction. And physicists, they have a prime suspect: the universe's relentless, unstoppable march toward disorder. The guy who actually came up with the name Arrow of Time was a British astrophysicist named Arthur Eddington way back in 1928. And he had this absolutely brilliant insight. He said, the only way physics can actually tell the past from the future is by looking at how random things are. If a system is getting more random, more disordered, then you know you're moving into the future. It's as simple and as profound as that. Now, the scientific word for this disorder is entropy, and the rule it follows is one of the most bedrock laws in all of science, the second law of thermodynamics. All it says is that in any closed-off system, and you can think of the whole universe as a closed-off system, the total amount of entropy, of disorder, always goes up. It never, ever goes down. That law is the real reason eggs don't unscramble. Let me give you a really simple way to think about it. Imagine you build a perfect, beautiful sandcastle. There's really only one way for all those grains of sand to be arranged to make that exact, perfect castle. But how many ways can those same grains be arranged into a messy, disordered pile of sand? Basically, an infinite number. The universe just naturally moves from states that are really unlikely, like a perfect castle, to states that are overwhelmingly likely, like a pile of sand. Your castle always ends up as a pile of sand because there are just so many more ways to be a pile of sand. And that, in a nutshell, is entropy in action.
So the huge takeaway here is that your everyday feeling of time passing isn't really a fundamental law of physics itself. It's actually a consequence of statistics, of things just moving towards the most probable state, which is disorder. This main arrow, the thermodynamic arrow, seems to be the boss. It's the master arrow from which all our other experiences of time flow. Let's see how they all connect. For example, our own sense that time is passing, what we call the psychological arrow, is a child of entropy. To form a memory, our brain has to create a bit of order, but to do that, it has to burn energy, which increases the total disorder of the universe. It all adds up. The same thing goes for the causal arrow, the simple fact that causes happen before effects, and the radiative arrow. Well, just think of dropping a rock in a pond. The ripples always spread outward, carrying energy away and increasing disorder. You'll never see ripples gather from the edges of a pond to shoot a rock up into the air. They're all just different faces of entropy. And here's a fun little curveball. While the physics is universal, how we perceive it can be totally different. Most of us think of the future as being ahead of us, but the Aymara people in the Andes see it the other way around. To them, the past is ahead because it's what you've already seen, it's known. The future is behind you because it's unseen and unknown. It's just a fantastic reminder of how our language and culture can shape something as basic as our perception of time. Okay, but this brings up an even bigger, deeper question. If the universe is always getting more disordered, well, that must mean it started out in a state of incredible, unbelievable order. Why? What was the reason for the universe to begin in such a special, low entropy state in the first place?
The answer seems to lie in the cosmological arrow of time. Our entire experience of time's flow, everything, is a direct result of how the universe started. The Big Bang wasn't just an explosion, it was a moment of incredibly low entropy, a highly ordered, very special initial state. And ever since that cosmic starting gun went off 13.8 billion years ago, the universe has just been unwinding, expanding, cooling, and getting more and more disordered. All the amazing things we see, galaxies, stars, even life itself, are just temporary pockets of order, created on the universe's one-way trip toward a final state of maximum uniform disorder, a state sometimes called heat death.
But, like any good mystery, this case isn't completely closed. That thermodynamic arrow is definitely our best explanation, but scientists are still out there on the frontiers of physics, investigating other, even stranger possibilities. For instance, could there be a unique quantum arrow of time hiding in the weirdness of how quantum possibilities collapse into one single reality? What about a particle physics arrow? We've found certain rare particle decays that are fundamentally irreversible. And maybe the most fascinating one. Does gravity itself give time a direction just by pulling stuff together to make galaxies and stars? These are the kinds of questions that keep physicists awake at night. The gravitational arrow is a perfect example of how science really works. The amazing physicist Roger Penrose suggested, hey, maybe time flows in the direction that gravity creates more structure. It's a great idea, but then another scientist, W.B. Bonner, came along and found a counterexample, a theoretical collapsing sphere where disorder went up, but the gravitational structure actually went down. And just like that, the idea had to be challenged and refined. It's a constant debate. And then there's this thing called the weak arrow. Deep, deep down in the world of subatomic particles, we found that certain events involving the weak nuclear force literally are not reversible. They break time symmetry. The catch? They happen so incredibly rarely that this arrow barely even points in one direction. It's a real fundamental crack in time symmetry, but it's way too subtle to explain the powerful river of time we feel every single moment. So we come all the way back around. Our deeply personal, profound experience of time moving forward, of yesterday being gone forever, seems to just be a side effect of a statistical trend. The universe is simply on a journey from an ordered beginning to a disordered end. Which leaves us with one final, absolutely mind-bending thought to chew on. If our sense of time is just an emergent property of cosmic messiness, is its relentless forward march truly fundamental? Or is it just our local perspective in a much bigger, much stranger cosmos than we can even imagine?